Oh, I see. Okay. Spread the spectrum. That's what we are going to do today. This, again, idling. Oh, okay. Great. Um, in earlier slide, somewhere, we looked at why the major difference pictorially between single peak signal and this spread spectrum, right? So we will look at that in detail today. And also, well, this module has another so spread spectrum is included. But actually, they are going together, right? You can see some of the black diagram so that data and signal can mixed together and modulated, encoded, compressed, encrypted, and finally can be radiated from the antenna, sender side antenna, and then receiver side antenna receives it, and then do everything in reverse way, so that finally you receive the same data in the same form as they were originally sent out. Okay, so they are very similar. Wi-Fi, cellular, satellites, almost all the wireless communications. The idea is very similar. But cryptography is a little different from one from another, right? Wi-Fi cryptography is not the same as cell phone cryptography, for example. So data that we are going to look at is digital data, and signal usually if it is a spread spectrum, then analog signals. But the example that we are going to do here is not analog signal. Why? Because it's not easy, right? I'm going to give to you how we could do spread the spectrum over analog signals. You can think of an analog signal as an example, say sine wave is the fluctuations, right? Sine wave, somebody hates trigonometry, but if we think of a sine wave, then where is my pen? Okay. When I bring up pen, then it's idling. Oh, see, my laptop has a problem. School needs to support me. What happens? It's gone? Hopefully not. Oh, okay. So we have sine wave like this, right? This is sine wave. Sine wave is very similar to cosine wave, right? Sine wave and cosine wave are converted. Sine wave can be converted to cosine wave. If we shift the phase a little bit, what degree? I think 180 degree, then it'll be sine wave will be cosine wave and vice versa, right? But anyway, this is not easy if we work on this. Therefore, sometimes we work on this, right? Digital wave. digital signals. When I saw you, I always think, oh, I forgot again. But I'll keep in mind. Don't worry about it. Okay. You had the due last November, I know. Okay. So spread the data. We need to spread the data over bandwidth somehow, right? General idea is this. If I have data, say 1, if it is a binary data, then I can combine 1 with any one of this. 1, 1, 1, 1, 1, 1, 1, 1. If this is the unit size. So all of these signals, I have data 1, 1, 1, 1. And another, the same size, I have, for example, next the data sequence is 0, then 0 will appear, 0, 0, 0, 0, 0, 0, 0, things like that. In general, right? It's a spread out, spread spectrum. In this case, if we lose this bit, then we lose, right? But if we lose this bit here, still we have so many other 1 bits. They're all the data. They are talking about the same one single data. That's what we are saying here. If we have some intercept, some data drops, and anything, any technical issues can be avoided in this way. What we want finally is simply this one, right? And from this another segment, we call that chip. There's one chip and another chip and another chip. For one single data, we make a chip, so we'll have multiple chipsets will be transmitted. So all the way that we modulate signals determines everything: data rate, transmission rates, accuracy. Although it is transmitted at high speed, if we lose some data, then it's not really good, right? It depending upon the application, right? So to make this spread spectrum, we have 2 approaches. Well, actually, one more today's lecture. We'll look at also CDMA, right? I know many of you heard of CDMA. It's not really the terminology recently used, but used up until 2-3 years ago. When you purchase a cell phone, then it's the CDMA time, right? So we'll look at that. Basically, to make this spread spectrum, we have 2 approaches. I'm going to do that over the frequency axis. I'm going to do that over time axis. Okay, I'm going to chop the time axis. So frequencies. I can divide the given frequency bandwidth into smaller channels. Okay, given whole bandwidth, you can split it into multiple channels. Not all channels will be used when I send the one data sequence, right? Similarly, direct sequence spread spectrum is I'm going to use uh, uh, time axis, time domain, but I'm going to put the data into multiple times. I'm going to spread the data over that time domain sequence. That's what we are going to do. Okay, so frequency hopping spread spectrum is the signal broadcasting over seemingly random series of frequencies. So we divide the frequencies into multiple channels, but the allocation of using the channels are random. So random number based frequency scheduling is the key issue. Direct sequence spread spectrum is that the bit can be represented by multiple bits of the signals. So for one data bit, multiple signal bits will be used, as I exemplified here, right? So they are all one bit appearing several times. So, for example, for one bit, if we have, let's say, 8 chips, so each small data set here is called the chip, right? Oh, here, chip encode. So, okay, so we'll look at that. The concept for spread spectrum is that input data fed into the channel encoder. So there is a channel encoder. The encoding technique will be discussed much in the second slide. We're now looking at a general idea of spread spectrum. And then another slide set is describing about channel encoding. What actually more general concept of encoding. So what input fed into channel recording is that it produces narrow bandwidth along signal around the central frequencies. So given the frequency band, it appears there in the center of the frequencies. Signal modulated using a sequence of digits. So modulation concept is being used. So we have a spread encode and sequence. So all details will be seen in a minute. So when the signals and data are modulated, pseudo noise or pseudo random numbers are used. They are very similar. Pseudo noise and pseudo random number. How can we generate the pseudo noise and pseudo random numbers? That is the key issue of this, right? It's not really randomly generated number. It is the number, almost random, but based on algorithm. If you know the pseudo random noise algorithm and the implementation or code for example, Verizon communication, then you know you can break in quick. And also we can increase bandwidth significantly. Receiver, so we send in this way, and receiver uses the same sequence, but in reverse ways. If it is modulated at the sender side, then it'll be a demodulation. If it is encoding, then at the receiver side, it will be decoding. The way the algorithm for modulation will be modified a little bit, therefore demodulation is possible. Similarly, encoding algorithm can be simply modified, therefore to be used for decoding, right? So we look at the cryptographies for, over wireless communications, which may be, so algorithms may be similar to general cryptographies, if you like, right? But the restriction for wireless cryptography is that many times sender does not have the same key as the receiver, and vice versa. So it is not just only asymmetric cryptographies, but encryption, but a lot more than that. Algorithms and key phrase needs to be generated at real time. So all that restrictions needs to be considered for wireless communications cryptographies. But anyway, we'll do that when it comes to that. And another concept is to increase, we'll that demodulation or decoding somewhere here. If it is encoding, then decoding is needed, right? So in this black diagram, this is general model, right? So we have input data, then initially channel encoding, and then modulation with the pseudo noisy generations. So it up to this point, it is spread spectrum. And it sends over the channels, right? Wirelessly, and the receiver receives. Then this part is well, all of this. From here, this is receiver side. This is the sender side, right? So modulation and encoding for spread spectrum signals can be performed in this order. Similarly, this is the reverse side, so that we will receive the same data it was sent originally, right? If you look at this, the way that we used here in this way is the reverse. We do this first and then go out. Okay, so if we have spread spectrum, then what is the benefit of that? First of all, it will be immunity, stronger immunity from various noise and multipath distortion, intervention, and interruption, including jamming. Clearly, you can see that if we have, for example, a certain frequency band, if we have data here, but if we spread that out like this, and the data appears all of this, right? Jamming maybe occurs here, so this is jamming, but we still have some, right? We can hide signals and encrypt signals. Um, Everything can be encrypted. Everything can be decrypted. So only a receiver who knows spreading code can receive signals. Real simple example will be discussed in the later slide. Several users can share same higher bandwidth with little interference. For example, therefore, that spread spectrum signals will be used for cellular, phone, and CDMA. So we'll look at this CDMA at the end of this slide. First of all, we'll look at our pseudo-random numbers or pseudo noise. It is generated by algorithm. To run that algorithm, initially some seed data needs to be provided. It is not non-deterministic algorithm. It's not stochastic. It is not well. It is deterministic, but it takes for not forever. It takes so long. If you want to break in, it takes so long. All data already gone, right? Oh, I found it. Okay. That's fine. Data successfully received and used about 2 years ago. Fine. If algorithm is good, then result pass reasonable test of the randomness. So depending upon algorithm, right? Pseudo random number, pseudo noise. It's not just a simple language that we can expect from programming language like Java, random. Python is random number generation. It is usually the random number can be generated by some probabilistic distribution functions, right? Poisson distribution functions. Simple distribution function is what? Uniform distribution function, right? Uniform. Well-known distribution function is normal distribution function, like a bell shape, right? So middle, higher frequencies, and as it go further, the low frequency, low occurrences, there's a bell shape. That's a normal distribution, normal distribution functions. There are so many distribution functions available. If any random number generated based on distribution function, then it is well deterministic and quickly captured, right? If we apply some distribution functions. So it's not rely on solely a function. It's more like algorithmic design. Okay. So the first way that we can see for spread spectrum signal encoding and modulation is frequency hopping. So frequency hopping spread spectrum. Signal broadcast over seemingly random series of frequencies. Receiver hops between frequencies in synchronized with the transmitter. Eavesdroppers hear unintelligible blips. Jamming on one frequency affects only a few bits. What happens? We'll look at this. Let me bring up this. What happens here is, this is a given frequency bandwidth. This frequency bandwidth. So we'll split the frequency bandwidth into n channels, sub-channels. So in this case, eight channels. For simplicity, all channels are disjoint. But in the real world, what? Last week we looked at. For example, if that is cellular signals, 802.11b, for example, then 2.4 gigahertz, around 2.4 gigahertz, there's some bandwidth, right? Can be from limited range of frequencies. We defined 14 channels. Each channel has bandwidth, a precise of a bandwidth. It should carry some data, right? If we make a smaller bandwidth of each channel, then what happens? We cannot carry many data sets. So we need to have a precise of channels. But we have the limited bandwidth, given limited bandwidth, frequency bandwidth. What happens? Then we have to, each channel should be somehow overlaid. If we really want non-overlaid frequencies channels only, then we do not have all 14 channels to be used. We need to use only a few of those. But in this example, let's assume that all disjoint. There is no overlapping. Although there are some overlapped, then we remove that in this scenario. So only all removed, right? That frequency appears here in this y-axis, from frequency 1 to frequency 8. Originally, I have these data sets. This is the data. This is a frequency bandwidth, but I have data. This data is modulated data. So not only signal, but data. Carrier signal and data signal together, modulated. So we have data piece 1 and data piece 2 and data piece 3 and so on and so forth. So this data piece 1 will use this channel 5. Data piece 2 use channel 8. 3 will use channel 3, and 4 will use channel 4. Okay, in this scenario, for example, eavesdroppers, that occurs in this frequency, for example, then only this. We still have data chip set 1, 2, and 3. We may lose 4 only. So partial, right? Jamming occurs, for example, frequency 3 and 4. It affects only these chipsets. All other chipsets will be fine, right? But at the receiver side, receiver should hop between frequencies for synchronization. For example, we received receiver here. It receives, say in this order. This comes first. Then we have to hop from here to there. This is number 1 segment. This is number 2 segment, number 3 segment, and number 4 segment. and number 5 segment, and number 6 segment, something like this. It should be hopping from frequency to frequency, right? There's a frequency hopping spread spectrum. What is the issue then? How can we allocate? For example, first data sets will be use frequency 5, next one use frequency 8 or 3, 5, whatever the frequency is. It should be, who will know that? Only sender and receiver. If somebody knows it, then can grab. Okay. Another beauty here is that color. Color. Let's say I'm going to use this color so that we have another data source. Okay. This is data source 1. This is data source 2. This guy also in this way. By the way, if it is a time, then this comes first, right? So let's say 1, 2, 3, 4, 5. Then maybe at this point, I'm going to use this for this number 1 here. While this guy use frequency 6 at time is a time t1, at time t2, why not? I'm using this, right? And time t3, I'm going to use that frequency and that frequency, another frequencies. Then we may have at most how many data sources? As many data sources as channels. 8 channels. I can carry all the data from the 8 different sources. It will be used only for frequency spread to spread. But in fact, it will be combined with direct sequence spread spectrum, and then also CDMA, and even further enhancement of CDMA. Basic operation is channel spacing corresponds with the bandwidth of the input. Each channel used for fixed interval. So usually 803.11, 300 millisecond intervals. Some number of bits transmitted using some encoding sequence directly by spreading code. And so idea is this. So what happens in this black diagram? If we have a binary data, then we need to first modulate it using some of the algorithms, right? Some key using this S means shift key. So bit phase shift key and frequency shift keys. So using some shift frequency keys, the binary data can be modulated. You can simply say encoded. Okay, it's not the same as the given data, but it is modified. Modified so that it can be easily spread out using some pseudo noise. What happens is the data can be modulated with the signal carrier signals, and then it can be ready to be spread. Okay, so in this way. So after that spread, then that is the outcome of here. So this process here is for frequency hopping spreader. See here, FH means frequency hopping spreader. And finally, some bandpass filtering algorithm is used. What happens here is that if it is analog, then signals something like this fluctuation, right? So somehow using some filtering mechanism, they're going to send only somehow in between. Drop all this because they're highly noisy, highly possibly noisy there, and even if we filter this out, we do not lose much data. We carry out all the data already, right? That's a simple example. At the receiver side, it's a reverse order. When data comes in, then first thing is that we need to do despreading. Frequency hopping despreading. So what happens here? If we have this, then by hopping, we need to reconstruct data 1, 2, 3, 4 from the red source, data 1, 2, 3, 4, 5 from the blue source, right? At the receiver side. And then according to that filter, we need to some algorithms, we can restore something like this. Something that we lost, we recovered. There are two kinds of FHSS, frequency hopping spread spectrum, slow and fast. If we look at the time, speed, the frequency shift time, and then data signal, data transmission time. Frequency shift time and data transmission time. So TS is data signal elements, and TC is frequency shift. Frequency means, in this case, channel shift, right? From one channel to another channel and another channel. There's some time, and there is also time for data transmissions. If channel shifting is greater than data, so data transmission time is smaller than channel shifting time, then at the data rate point of view, everything goes slow, right? But our main primary goal is to send the data, right? But there is a longer time of channel shifting, then that much slowly data can be transmitted. The other way here, then that is a fast. Channel shifting time is so quick, so small, smaller than data sending time. Then what happens here is that if you look at this and that, this and that two slides, compare very carefully, then you will see this is a random pseudo noisy sequence. So we have noisy sequence 0, 0, 1, 1, 0, 1, and so on and so forth. This is input data sets. This guy from one frequency to another frequency, this is time, frequency time is longer than data, which means overall data, if we send all of this, then it takes a longer time, right? Compared to this, data shifts very quickly. I mean, the channels shift very quickly so that we can send, hey, this short time we send 0, and then next 1, and next 1. If we see this, if we compare this with the previous, then what happens? This whole thing is, look at this, 0, 0 is this. So overall data slows, right? This is much faster. That's what happens here is that channel shifting time is shorter than data sending time. So data. It's not really data sending time. It's more like speed, right? Data speed is faster than channel shifting speed. This is vice versa. This is the other way. Channel slowly. I mean, it takes longer time. So okay. Performance, typically large number of frequencies used. If we have so many channels, then frequency hopping, I mean, depending on what is the performance of FHSS, then it depends on the number of frequencies. Because frequency shifting affects the data sending speed. Okay, this is frequency hopping spread spectrum algorithm. Any questions? But we do not have an example exercise for this frequency hopping spread spectrum. The idea is very simple. Only the issue here is a pseudo noisy. Pseudo random number should be efficiently generated. So depending upon the algorithm. So we do not learn that algorithm here. But I want you to understand the general idea of frequency hopping spread spectrum. So clear, right? Simple. Now, direct sequence spread spectrum. So each bit of data can be represented in multiple bits of carried signals. Spreading code spread signal across wider frequency band. We don't care here the frequencies. Okay, so different angle of different algorithm for spread spectrum. Different algorithm, different approach for spread algorithm. Spread algorithms depends on the viewpoints. For frequency hopping, is considered in the frequency axis. On the other hand, direct sequence is more time axis in over the time domain. So why not look at the channels, but you can see more clearly. Oh, this is the signals, right? For example, like this. So over the course of time, you will see some of the code here. This is the data. Say this data is somehow already mixed. Okay. Doesn't matter if it is a real input data or modulated data. See here, we assume it is already modulated. Now we are looking at spreader. So if it is 0, and then pseudo-random number bits stream, let's say this is a signal, okay? Data and signal. Then how can we have transmitted the data? By combining these. So this is the data sets, this is our signals, and what will be our what can we send by combining those two, right? This and this together mixed, therefore real data to be sent is this. If that is received like this, this is exactly the same as that, right? This and that are the same. Because this is sent, so we receive that. When we receive this, we know also the stream, bit stream, which is a signal, like a carrier. What is a signal? If we see simply here, then I think from here to here, right? From here there, right? Are they similar? From here, there. From my observation. So this is a chip set. This is my carrier. This is a bit stream, random number generated bit stream. So bit is generated 0, 1, 1, 0, 1, 0, 0, 1. Again here 0, 1, 1, 0, 1. It's not really the same. But anyway, if it is the case, right? It's I think longer than that. It repeats. All right. So we already know this. This is a known. So this is a known, number 2 known. Number 1 is the data that we send. And this is received. Something received from something received. If we use something we know, then we can recover the data. This data is the data the sender sent out. Back here. Therefore, spreading code spreads signal across a wider frequency band in proportion to number of bits used. 10-bit spreading code spreads signal across 10 times bandwidth of 1-bit code. So in this example, if we want to send 1 bit of data, we use a 10-bit spreading code. I'm not sure that is the case here. Let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bit. So if we somehow chop here, then 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, I think here, 0, 1, 1, somewhere here. 0, 1, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0. Is that right? I found it. Let's see. If I do, I want to change the color here. This from here there, that repeats, right? 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1. I think up to here, right? 0, 1. Somehow confused. But anyway, so that's 10-bit. For example, 10-bit spreading code spreads signal across 10 times bandwidth of 1-bit code. So method is this: combine input with the spreading code using exclusive OR. Input bit 1 invokes spreading code bit. Input 0 bits doesn't alter spreading code bits. Data weight equal to, so performance is similar to FHSS. So what happens here? If this is the data, this is the code that we are looking at. Let's see, highlight. Let me use this. So I'm going to use this using 4 bits, using 4 stream bits. I'm going to spread 0, data 0. When I spread this, I'm going to use exclusive OR. What exclusive OR means, if I have 0, this will apply the 1 at a time per bit. So 1, 0, 0 and 0, exclusive OR is what? 0, right? Exclusive OR, those who do not know, I'm going to say that here. If we have exclusive OR operation, if we have same bits, then it returns 0. If we have two different bits, then it returns 1. What happens here is if we have 0, 0, then it returns 0. If we have 1, 1, it returns 0. These 2 bits, right? These and these bits. If we have a 0 and 1, it returns 1 because they are different. 0 and 1 returns 1. If we have 1 and 0, then it returns again 1 because they are different, right? So if you see here 0 and 0, they are the same, it returns 0. If we have 0 and 1, 0 and 1, it returns 1 because they are different. 0 and 1, they are different, it returns 1. 0 and 0, it returns 0. Again, if we have 1 and 1, it returns 0 because they are the same. 1 and 0, it returns 1. They are different. 1 and 0, they are different, so returns 1. 1 and 1, they are the same, so returns 0, right? So all the way. So this data is returned, received at the receiver side. Once you have this bit stream, then you apply again. What happens here? This is 0. This is 1, right? 1, 1, and 0, 0, 1, 1. What happens is that if there is a 0, then we we increase the voltage. If it is 1, no voltages. That's what how it was sent, right? Here. If it's 0, then voltage. So we have some voltage. If it is 1, then no voltages. 1, no voltages. 0 volt. Say 5 volt, 5 volt. 0 volt, 0 volt. It's up to the device. Usually 0 is yeah, in this case usually in this wireless signals 0 means some high voltages, 1 means low voltages. Sometimes it is a positive voltage or negative. So 0 maybe 1 volt, 1 negative 1. So 1 volt negative 1, 1 volt negative 1, things like that. So 0 means, so that when it receives, we have, according to the signals, if there is a voltage, then we can say 0. Let's say plus 1 volt or negative 1 volt. If it is negative 1 volt, then 1, positive 1, 0. So we received these signals, right? And we already know this. So using this signal, we applied whatever the same number here. Same number. I'm going to use the different color. What color that we may be able to use? Here, purple. So anyway, this is the same. This number 2 is the same as that number 2. So what we want to do is, I'm going to apply this. 0 and 0, they are the same, so it should be 0. Right? High voltage 0. 1 here, 1 and this 1. Therefore, 1 and 1, there's a 0. 1 and 1. 1 and 1, same. Yeah, there's 1, right? 1 and what? It should be 0. Oh, we are talking about here. So there is a 0, right? Here. So 0. This is what we want to. This is what we want to find, right? 1 and 1, they are the same, so it'll be 0. Yeah. Right? So 0 and 0, they are the same, so it is 0. So at the receiver side, what we have is 0, 0, 0, 0. Send 1 0. Receiver receives 4 zeros. What does that mean? So spread out, right? 1, data 1 originally sends 1 0, right? When it receives 4 zeros. Right? If we have here, so for 1 bit, 4 chips used, then we need to divide that by 4, number 4. Say this is 1 volt, right? Voltage 1. Another voltage 1 here. Another positive volt. Another positive 1 volt. If we add them, then positive 4 volts, right? Because we have 4 chips used to represent 1 data bit, so we need to divide it by number of chips. 4 divided by 4 is 1. 1 volt, positive 1 volt. What is a positive 1 volt? that means data 0, right? That's what we have. I'll give you time. So you have to see. If you know this, then you know everything that we need to know for today. But the other concepts are similar. CDNA is based upon this and same thing. Right? Okay. Let's in the previous the lecture. Uh, this is cleaned out. Um, so uh, as a summary, in the following slide, if we look at the receiver side, or it doesn't matter, because they are using the same operator, exclusive OR operator. If we have two data, SD, this is a signal and then CT, this is a chipset. So signal and chipset together can be used to spread. The operator to be used here is exclusive OR. So you will have this. This operator, exclusive OR, is used for sending and receiving together, which is nice. And this exclusive operator will be highly used for wireless communication, because a simple operator will be used at both sides, right? Same thing here. This direct sequence spread spectrum can be used for example, real cosine signals, sine signal, cosine signals. If we have a bit phase shift keys to be used. So a lot of theories discussed here, but you do not have to understand all of this, right? In pictorial representation here is that if we have data here, data here is not really zeros and ones like binary data, but rather it says positive 1 and negative 1. You can simply say positive 1 will be zeros and ones, but usually positive 1 is representing 0 and negative 1 for 1, right? So we have, say, voltage here, some energy. If there is a positive 1 volt and negative 1 volts, things like that. So we have, instead of another digital signals for carrier, so that we have a chip, multiple chips, but in this case, simply signals. But there is a shift. There's a shift here. There's another shift here. This is a phase shift, right? Phase shift. This is a phase shift. And depending upon this phase shift, we have a different code. And similarly, we can restore that data. This is when we use phase shift keys. The idea is very similar, but only the function is different, whether it is analog data or digital data. The idea here is DSS signal is given this signal energy, then it can be spread out like this. Okay. With the frequency hopping spread spectrum and direct sequence spread spectrum are the ideas from both together. Now we can think of a code division multiple access, so-called CDMA. The underlying idea is very similar, but if you see here, we can mix multiple different sources into one code by dividing code. Let's say code 1 from one source, code 2 from another source, code so on and so forth until code n. Okay, so data from multiple different sources can be modulated and finally restored. Okay. So multiple sources coming into our antenna, and then it is well, this is the receiver side, right? But sender side is idea is similar. When you receive multiple code together, so they are all together like this. This is comms. Originally is n different codes, but they are all together codified. This is received, then we need to do despread, so that part of this is for code 1, part this is finally code 1, and this will be the code 2 and code n. Right? So we will look at that. Basic principles of CDMA is that D, that is a data rate, break each bit into K chips. K chips means we have a carrier signals. So how many, let's say for one data bit, it's the data. How many signal bits that we want to use to mix? So K. We call this K chips. Okay. It's very natural to spread one bit over K spaces. We call them K chips. Chips are a user-specific fixed pattern. User-specific means depending upon the devices. This pattern is called the user code. The code are orthogonal. Chip data rate. This is a data rate D, but over the channel, the rate is channel rate should be computed KD chips per second, because we have K chips to represent D data sets. Then anyway, everything K times D chips needs to be transmitted. So CDMA example is this. Let's say if K is 6, which means we have 6 bits to be used to represent one data bits, right? So zeros and ones. So our chip pattern will be like this. Chip 1, chip 2, and chip 3, chip 4, chip 5, chip 6, chip whatever that is, right? And for each 1 bit, 8 sends user code as a chip pattern like that. For each 0 bits, 8 sends complement of user code. It's a complement. If that is a C1, then negative C1, because we need to distinguish 1 from 0 and vice versa, right? Receiver knows sender's code and performs the decode functions. So example, this is example for today. Given we have a spreading code K chips, and then user message D, and then source, we have N sources. How can we mix them all? Spreading data, spreading message over the signal code is to use XOR, exclusive OR operator. We combine them, adding all the voltages. And then how can we decode? Decode is, we need to multiplication. As we see here, we do multiplication. We multiply all and add them all. Multiply that and then divide. How many code? No. How many chips are used? So we divide that by K. Then that is encoded. So this is an example. We have a spreading code 0 1 0 1 0 1 0 1. That is a carrier. 0 1 0 1 0 1 0 1 0 1. It repeats this code like this: 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1. It flows continually as spreading code flows. Message will ride on it in our language, but technically we modulate, spread them. How? 0, so first 0 sit on this, and next 0 sit on another, like this. So for one set of spreading code, another set of spreading code. So this, see here, 4 chips, right? 4 chips to represent 1-bit data. In other words, 8 chips for 2-bit messages. For one user, right? For one source. So 0 0 0 0 0 0 0. So 0 mixed here with that, and another 0 mixed that. We exclude the exclusive OR bit by bit. Then 0 0 means 0 in exclusive OR. 1 0 means 1, right? 0 0, they are the same. So 0, 1 0, that is 1. So eventually, if we send the 2-bit message, then how many chips? 8 chips, right? To send the 2 bits, messages, we use, eventually we have 8 chips to be sent out. This is for user 1. So there is another user. Spreading code is 1010. Previously 0101. Doesn't matter, right? 1010. That is what the code is. So we have 1010 and 1010 and 1010 and 1010. So first code 1 sit on this, and second code in the second chipsets. Exclusive OR. So 10 means 1 in exclusive OR operation. 00 because they are the same returns 0. 1 and 0 because they are different, it returns 1. So we have 8 chips again. Similarly, we have another message from another source which has different spreading code, of course different messages. Idea is the same, chipsets, so we can send more and more, right? More and more. We apply exclusive OR. 0 and 1 returns 1, 1 and 1 returns 0, and so on and so forth. All three together. We have user 1 data and user 2 data and user 3 data, right? Let's assume that these all three data chipsets will be shipped out from one device. You can simply imagine that you have text data, voice messages, and some music that you want to send from your cell phone. One device, same device. Okay. So your device generates some voltages, energies, so that energy will propagate through the antenna. Simply, in our case, if there is a chipset is 0, then we high voltage, we send out high voltage. Chipset 1, then low voltage. The data from the chipset from the user 1 is this. Chipset from user 2 is that, right? Chipset from user 3 is this. So that according to this device, we need to generate the signals. 0 means positive 1 volt and negative 1, right? Volt. Positive 1 volt. 0 means positive 1. 1 means negative 1, right? And 0 means positive 1. Negative 1, positive 1, negative 1, positive 1, negative 1. User 2, because we are using the same device, same cell phone, so 1 means negative 1, 0 means positive 1, negative 1, positive 1, positive 1 is 2 chipsets, and negative 1, positive 1, and negative. From user 3, the chipset from user 3 is negative 1, negative 1, positive 1, negative 1, negative 1, negative 1, positive 1, and negative 1. They're all voltages. So you have a voltage 1 and voltage 2. Therefore, we're adding them up. So message will be, this is a positive 1, positive 2, and positive 3. So positive 3. So 3 volt, 2 volt,
1 volt, 0, and negative 1, negative 2, and negative 3. So these are the negative 3 volts. If we add, see here, positive 1, negative 1, and negative 1. I think this is a 0. This is negative 1. I'm sorry. Let me clean that up. Erase, 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 erase. So real story is like this. I think this is a 0. This is negative 1. We add them all, then there's a negative 1, which is this, negative 1. And then negative 1 here. I'm sorry, this is not even 0. That is positive 1. This is positive 1. So 0 is here. This is a 0. 0 volt. So one below and one below, one up, so 1 volt, and negative 1, positive 1, and negative 3, and positive 3, and another negative 3. So this kind of signal will be shipped out. This is digital signals, right? That signal ships from your cell phone. So what does it send? It sends these signals. See here, negative 1, negative 1, positive 1, negative 1, positive 1, negative 3, positive 3, negative 3. This signals is sent out from your antenna, and at the receiver side, it receives this, right? So what it receives here is a negative 1 and positive 1 volt and positive 3 volt and negative 3 volt, right? So in this sequence, so all mixed, all mingled together. How can you restore the data separately? If that is a voice and voice message, if it is music, text message and text messages, right? What it does here is we apply chip what is it? We apply the original spreading code 0101. So we use that 0101. This, okay. So 0 1 0 1 0 1 0 1. User 1 code. Oh no, we don't do that. This code. We are playing with the voltages, right? Volt. So so what happens here? Yeah. This one 0 1 0 means if we convert this to volt, this 0 means 1 volt, 1 means negative 1 volt, 0 means 1 volt, 1 means negative 1, right? So on and so forth. So this is nothing but, we need to convert this to energy. This is 0 means 1 volt, 1 means negative 1 volt. We still use the same algorithm here, right? Same policy. And that. And these all come from that spreading code. So we know spreading code, which means text message has a specific spreading code. Music has its own spreading code. Voice its own spreading code. So we use that spreading code here. But because we are now dealing with the voltage, because we're still in a device, so we need to convert that to the voltages, and then we'll multiply. So multiply. -1 times 1 means -1. -1 times -1 means 1. 1 times 1 means 1. -1 times minus is 1. 1 times 1 is 1. -3 times -1 is 3. 3 times 1 is 3. -3 times -1 is 3. Actually, these 4 chipsets for one data, right? So these 4 chipsets for one data, these another 4 chipsets for another data. So what we need to do is we need to add them all. -1, +1, +1, +1, then there is a 2. We add them. 1 plus 3 plus 3 plus 3, then 10. We divide that by 4 because we have 4 bits. Right? If it's positive, then there's a 0, and also there's a 0. Right? We use this same concept throughout whole. Okay. That's what we need to do. Okay. There's a CDMA. So I'm going to, based on this, I'm going to give you very similar but very clear homework assignments, so that CDMA algorithm will be assigned to 3 different data, message data. I'm going to give it to you. Same thing, spreading code. Okay. Any question? It's very straightforward. It's not simple, but worth a try. No, all different, right? Yeah, depending upon device, right? If you have 8 bits, then you have more.